if you will recall, the goal is to show okay, for each I, this is the player, the distribution is continuous and strictly increasing. Then there exists a NV free partition of the NV free partition into intervals, right. Okay, the cake is this 0-1 interval, right? Closed interval. Okay. So, the way we were in order to show this, that this particular proof is from 1999 by, so I will write the, when it came out it was quite a it was seen as a wonderful exposition of application of Sperner's lemma into something that seems sort of unrelated, right. So, I will give the full paper, name of the paper and where it came about and so on later, but so the goal, so the point is to basically where does Sperner's lemma come into play? In order to create this intervals, we basically think of the cake as being something of a simplex and partition that simplex into these pieces, and I will sort of write the. So, the goal today would be, if nothing else, for you to understand the entire sort of the broad contours of the proof, like what is actually happening, and then I will fill out the details in the second part of this lecture. Okay. So, the thing is to visualize the cake as some type of a simplex, and the simplex can be subdivided into smaller simplices, and such that we will show, we will argue at least, that there exists a way to partition which will basically be this epsilon NV free partition. And additionally, if the function f I is continuous and increasing, that epsilon NV free partition that can be shown to also be NV free. Okay. So, that is the idea. So, where so this is why we are even talking about simplices. We made it seem like a conceptual jump from cake to simplices. That is the sort of thing that we relate the cake cutting problem to subdivision of simplices with some additional property. So, any kind of subdivision is not going to be enough, but a subdivision which has some nice coloring properties, that nice coloring property, why it exists, how it exists, we will talk about it. Those nice coloring properties allow us to assign a piece of that partition to a particular player, okay, and in a way that basically bounds the NV to epsilon. That is the main outline. Okay. So, let us just briefly recall, we agreed that we said that okay, simplex is a convex hull of a n simplex is a convex hull of an n plus 1 points, any points in the real Rn, Euclidean space Rn. So, you can think of if you are confused at any moment, go back to a triangle. A triangle is a, so shown via, I will just sort of a special subdivision of a simplex. Okay. So, think of a, I will show many sort of colorful pictures of a triangle. So, always think in terms of a, this is a 2 simplex, okay. given described by, let us say, vertices V0 or points V0, V1, V2. Okay. That is the this thing, right. So, this is like this arrow that or vector that connects V0 to V1, this is the one that connects V1 to V2, this is the one that connects V0 to V1, and because we are going to create we need a convex hull. So, basically it describes a triangle, that is the idea. Okay. So, it has to be that the 3 vertices via which you are creating the simplex are affinely linear. Affinely linear means if you subtract the point V0 from each one of them, they are linearly independent, and the such points, these are the only points that can potentially create a simplex, and from that the simplex is described by its convex hull. Okay. So, when you give a set of points, the convex hull gets sort of uniquely described. Okay. So, that is the details of it. Now, K face, quickly speaking, one face of a triangle are the sides, the inside is the 2 face, and so on. Okay. We need a little bit more detail. Now, the one face of a triangle can be of 2 types. Okay. They can be an inner face or an outer face. This is an outer face, but imagine this triangle can be divided into smaller triangles, anything. Okay. Then these orange ones are this thing, outside ones are outer face, and these things inside are the inner face. Okay. Okay. All right. If you, as always, please stop me if something is not clear, otherwise since we did all those things, I am going a little bit quicker. Okay. So, yeah, you can see this picture, it is this triangle, and yeah. So, this triangle can be divided into smaller parts. We will see what that kind of division is. You can't just split it any way as possible, but if you do it, then you can see these smaller triangles emerging, right. They are also simplices, they are also 2 simplex because they are a triangle and they satisfy these properties, and you can sort of talk about their faces. Now, the important thing is, if you now we will, this is an important definition. Okay. A subdivision of a simplex is a collection of smaller simplices of I mean, it is still an n simplex, but it is still a it is sort of like it is contained within the bigger simplex. Okay. So, within a triangle you can have smaller triangles, and notice these triangles can be like weirdly constructed, right. They do not have to be, invariably when I draw it, they tend to all look like equilateral, the same size and so on, but you can have like sort of as many kinds of this thing. So, this is also, these are also triangles, right, and they are also a simplex, simplex within the bigger simplex and so on. So, now this sort of breaking down of a simplex into smaller simplices is called a subdivision if that breakdown has additionally satisfies 2 properties, which is that either each of the smaller simplices, okay, they are vertex disjoint, they are disjoint, okay, disjoint meaning they have nothing in common. So, for example, this one and this one, there is nothing in common, right, they do not share any edges and so on, or if they do have some intersection, it must be along a face. So, a face can also be a vertex, by the way. A vertex is a 0 face. So, this and this triangle, for example, they have, oh, they also have one edge. Okay, so this one, this tiny one and this one, they share a vertex, right. So, this is a valid this thing. So, what you do not have is like this is a triangle, this is a this sort of thing does not happen. Okay. So, yeah. Okay. So, subdivision of a triangle is sometimes also called triangulation. Okay. Just a sort of terminology thing. Okay. So, now okay. So, we will talk about these sort of definition, sorry, okay, I said everything that I wanted to say. Okay. So, now with these some of these details, this definition in mind, I am just going to write down the basic idea behind the proof, okay, main steps, and then we will invoke it and fill in the detail. So, we start, consider, okay, you know standard basis, right? We consider the simplex defined with the standard basis in Rn, okay. So, EI is this one. So, you have 1 in the ith position, that is what we call a standard basis, okay. All right. So, this is basically an n minus 1 simplex, this delta, if I define it with n vectors, okay. There is a, you can't, okay. Did somebody ask something? I can't, okay. I can't see the zoom. Okay. Dipro, can't you speak up? Otherwise, I might miss questions. Oh, they are not. People can't. They can't be heard. That's what Sanjay is saying. No, Dipro, you're not. Dipro, you're not audible. So. Can you hear me? No, they are not audible.
No, they are also, I am hearing them.
Dipro, can you speak? Can you say something?
I will keep it for you.
Oh, okay. So the okay, yeah, we can't hear you. I guess you guys can hear me. Okay, okay. Now, can you say something, Dipro? Really can't hear anything. Yes, now there was a bit of a. Yes. Now I can hear you.
It is better, right?
Yes. Now it's okay.
Yeah. So I was asking, when we say face, so does it mean like a dimension 2 thingy?
No, face can be of any. So if you are talking about a n minus 1 simplex, you can have a face. So let's maybe go back to this formal definition. So you can have a 0 face, you can have a 1 face, 2 face, 3 face, all the way to n minus 1 face.
Okay.
Okay, so this is just to draw, to be able to draw on the board. So the triangle is like the biggest, the most general picture I can draw on the board. You can imagine a tetrahedron. So on the floor, wherever you are sitting, imagine a triangle drawn on the floor. Okay, so take 3 corners and draw a triangle. Take the 2 sides of the room and draw a diagonal through this. Now imagine a 4th point somewhere along the height of the room. Okay, so this is the 4th point, and the 3 points are that corner, and this corner. Okay, so now draw lines connecting all the corners to each other. What you have is a 3-dimensional shape, and this is a 3-dimensional simplex. So here a 0 face would be the vertices, 1 face would be these edges of this. So each side, if you think of the flat surface of this particular tetrahedron, is itself a triangle. The edges constitute a 1 face. The triangles that form the flat faces of this tetrahedron are a 2 face, and the entire tetrahedron itself is a 3 face. Okay. All right. I hope that I can't hear you now. So, okay.
Yeah, I understand. Thank you.
Okay. Now only the n minus 1 face has the special name inner or outer face. Okay. It is just a matter of it is easier to I mean we will sort of use it, that terminology. So, it is sort of worth it to get, I mean it kind of intuitively you understand what an outer face is. It is like you know if I break this tetrahedron into smaller tetrahedrons, the faces that are on the outside of the bigger tetrahedron, those are the ones that constitute the outer face. Okay. And anything that is not on the outer face is essentially basically an inner face. Okay. So, okay. With that, let us just talk about the main steps of the proof. Okay. So, first I considered this simplex. I say there is a way to there exists a subdivision. It is a very special kind of subdivision, and we will say how do we get to there exists a subdivision of delta such that that each simplex subdivision, let us call this the gamma. Okay. We will refer to this subdivision, meaning the collection of the smaller simplices as gamma. Okay. That is what I mean by gamma. Each simplex in gamma, let us call it has small diameter. Okay. Meaning each simplex, I can subdivide this bigger simplex into smaller and smaller, like as small as I want, smaller simplices. Okay. So, that why am I doing smaller? Basically, I need this condition that there is a way to do it that creates these smaller simplices. Okay. Bounded diameter. Now, just as a matter of thought, there might be multiple different ways of subdividing so that to create a smaller diameter. Okay. In particular, this picture itself I could create many different subdivisions. Okay. The problem is not every such subdivision will lead to the property that I need from it in order to make the proof go through. Okay. So, we will describe this subdivision in a very particular way. Okay. So, this is why I am saying there exists a subdivision. What are the details of it? We will look at it little later. Now, this subdivision when I say subdivision orally, I am basically talking about both the collection as well as the individual pieces. Okay. The simplices, so let us call it the vertices of the subdivision in gamma can be properly colored using, how many colors do you think we need? N, oh sorry, okay, n plus 1 colors. Okay. I will tell you, can be properly colored. Okay. There is a way of creating the subdivision. From there is a way of creating a coloring, that is a proper coloring. From there we extract from that coloring, okay, where we define what we call a Sperner labeling, a valid Sperner labeling. I will say everything. Okay, properly colored basically means if you have a simplex like this, all the 3 vertices are distinctly colored, have distinct coloring.
Okay, we are coloring vertices.
Yes, yes, the colors are associated to the vertices. So, when I am subdividing, I am creating these smaller triangles, right. So, I am actually creating newer vertices. So, they will be internally they will be colored by one of 3 colors. Okay. And when I do that one of 3 colors, there is a way of doing it which will give a proper coloring. Okay. I will fill out these are just so that you see where all the details are, and so that we will fill in the details in each step. From there we will extract what I will define to be a valid Sperner labeling. Okay. This would yield this thing delta star that is fully labeled. Okay. Now, using Sperner's lemma, we will infer a epsilon for any given epsilon NB free partition. Okay. These are the steps that we will take. I will tell you what is Sperner's lemma in n dimension. We saw in the class during the pipette completeness Sperner's lemma in 2 dimensions. Now, we will talk about in 3 and n dimensions and so on. Okay. So, I am yet to give lot of details, but is the contour of this proof clear? If it is not, just please ask me.
We are coloring a valid subdivision, so can't we manage to do it in lesser colors?
What would fewer colors actually mean?
4 or 5.
Why sorry 4 or 5 in what case? For even when n is 100?
No, okay, let's put it.
Yes, that is the thing. Whatever this n is, this is related to that. Okay. So, triangle is a 2 simplex. It requires 3 colors to be properly colored. The notion of proper coloring here is, well, we will infer a graph in which you will see what is proper coloring means, that there are no edges which share the same vertex, right. But if you have a triangle, you know how many colors do you need to color a triangle? You do need 3 colors, right. So, in order to properly color a clique of k size, you need k colors. It is sort of the same thing. It's exactly the same thing. But the point is, no matter, see, but I am not dealing with one triangle here, right. If it were one triangle, I just put color 1, 2, 3. I am saying no matter, there is a way to subdivide that even the smaller triangles inside are properly colored.
In 3, that triangle is
Why is this not properly colored? This is properly colored.
like if we put a vertex in between.
Yes. So, we will keep on doing this as much as possible, that is the thing, like as smaller the dimension this becomes, this would be this would have to, if this is just this thing, then this would have to be 2, right, and then basically this would also be subdivided, this would be subdivided, and so on and so forth. There will be lots. So, we will see the picture of it, but if you remember in the pipette completeness proof, what did we have? We had an outside boundary valid, we had a rule to color the boundary vertices of that grid. And then we said inside you color howsoever you want, there will always be a trichromatic triangle. Okay. So, the point is that is essentially what the Sperner's labeling does. Like the Sperner's lemma says that as long as you have some Sperner's labeling, okay, the valid Sperner's labeling, the Sperner's lemma will hold, and we will be able to find, I will tell you exactly what it means in terms of a simplex in n dimensions. The point is, we are just applying Sperner's lemma on a Sperner labeled simplex, that is a delta star. How we get the Sperner lemma basically uses an earlier step where we create a subdivision which can be properly colored. Okay, so, the details here matters, like when we are applying Sperner's lemma. If we did not have this earlier step, it is not clear why applying Sperner's lemma would directly would actually yield an NV free, epsilon NV free partition. Okay, all right. So, with that in mind, I do not think, okay. One very important step here to note is the following. Let us write here. I say, and it is hard to any point x, okay, in n dimensions describes a partition of delta. Do you see why? Let us again talk about smaller dimensions. Okay? Let us talk n equal to 3. Let us take a equilateral triangle. Okay? A point here is this. It has some x1, x2, x3 coordinate. From here, I drop a perpendicular to all the 3 sides. Okay. Do you see the 3 partitions? This, this, this. Okay. No matter where you draw this point, wherever you draw this point, you will have a similar object. We are only talking about point in this. A point in the simplex describes a partition of the simplex. This object, this property you can also visualize in on a tetrahedron. Take a point which has all the 3 x1, x2, x3, this thing, and what happens then? So, if this point you basically drop a perpendicular to each of the bounding sides, you will get 4 chunks, like the whole object will be divided into 4 pieces. It is easiest to obviously visualize over in a triangle.
There we are dropping a perpendicular on 2 faces or 1 face?
This thing, you drop it over the 3 faces, like the 2 faces. Sorry, the triangle are 2 faces, right? So any point, just this, 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 this. Correct? So this is a very important part. So what are we actually trying to find in all of this is a point where each of these pieces have NV epsilon bounded NV. Basically each piece will be given to the 3 players, okay, and the way we will color the vertices will tell us which piece goes to which player. Suppose if this were colored C1, this chunk, whichever piece that contains this vertex will go to that player. If this is colored, we need 3 colors, and 3 colors is sufficient because we actually just want to create a partition among 3 people only, right? The cake has to be divided into 3 people. So this part then would go, whichever part that contains this would go to the second person, second player, and so on. Okay? So the goal here entirely is to create a appropriate such point that will partition the whole simplex into epsilon NV bounded pieces. Okay? All right. So let's. I don't think I wanted to say anything. Okay, so you would recall what the definition of epsilon NV is. I am not writing it. I am going to write the assumption here, which is sort of important. It is okay. Each n people prefer 1 epsilon NV. 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 1 to new place. Just a minute. And A is of course a subinterval and so on. Okay. Okay, for all, I should write it. Okay. Okay. So, maybe we can see a picture. Let me try to draw this picture of okay. So, in a cake, if there are, I do not think this is particularly helpful, but okay. I just I do not agree this particular picture is useful. Let us just try to follow with the abstract ideas, and then we will see we will try to simplify wherever needed, but otherwise let us just go with it. Okay. You were going to say something?
Like half part of that picture was not visible.
Which part?
The one you just.
Oh, it is okay. We do not need it. I do not think it particularly helps to say that. Okay, how should the cake be divided? It is clear that what we want to do is to cut the cake into these continuous chunks. Like you do not give a part here to a player 1 and another piece from there to player 1 again. You just want to create continuous chunks. Okay, all right. So let us now get to this thing. Okay, now. Okay, so this result is this is what so for any simplex and epsilon greater than 0, you can, there is a subdivision delta such that all simplices in delta have diameter less than epsilon. This is the subdivision that we are describing here. Okay. So, the way to describe this subdivision is this thing called the barycentric subdivision, which we started with last class. Okay. So, what is this? It is very simple idea. I think I have to use some board space. So, you have, so okay, so I am just going to shuttle back between the, so here we are going to apply this result to the type of simplex we have defined here, which is on standard basis, okay, E1 to En. It, so do not get confused with what is n here and what is there, it just like the n here is, we are just indexing differently and so on. The main idea here is the following. Let us just use this. Whatever are the points so this is the, let us say, simplex on E1 to En. Okay. So, you take any subset of this. Okay, let me just describe the subdivision maybe as a more general object, it does not matter. Okay. So, this is n union 0. For any such this thing, you can associate with S, or rather corresponding to S, there is a one face, there is a S minus 1 dimensional face, okay, which is basically the convex hull of the points that are indexed by S. Okay. Okay. Okay, it does not matter, when we take the entire subset, basically we get back delta, right. if you take all V0 to Vn, you will get back delta. So, that is not this thing. So, you can think of it this way, but with each S which is a subset of the indices, look at the convex hull of the vertices that are identified by S. Okay. This is what? This is a S minus 1 phase by a definition. Why? The size of S y, correct? Okay. All right. So, tell me, so suppose I take the vertex V0, it is basically corresponding to the set S0. So, let us take an arbit2, I have a, okay, let us take S0 is, let us say V1, S1 is V1, V2, S2 is V1, V2, V0, S3 is, let us say, let us talk about and this is, and let us say n is actually 3. Okay. All right. This is a subset. I should actually say 1, because S strictly speaking is a subset of indices, correct. But this is the point of it, that it does not matter, they can be looked at interchangeably. Okay. So, corresponding to this, what phase do I get? V0, V1, this itself is a phase. Corresponding to this, what phase do I get? Huh? Yeah, the line connecting V1, V2. So, let us call it V12, okay, just this thing. This is V120 and V12, okay, 03, maybe I should 012 or so on, okay, does not matter, right. Okay. So far so good. Now, okay. So, suppose the barycenter of a face is defined by this. So, these are the faces. Okay. This is the arrow, means this is the corresponding faces. So, the barycenter of a face is defined by this. You basically sum up all the values that correspond to this. So, the barycenter of this would be just V0. This would be V1 plus V2 by 2. This would be V0 plus V1 plus V2 by 3, and this is V0 plus V1 plus V2 plus V3 by 4. Okay. Yes? Okay. Now, this is the interesting part. Okay. I am going to draw a graph using the faces as the vertices. Okay. So, the vertex V0 has an edge to all the vertices that contain it. So, it should have a vertex to V1, sorry, you guys have to correct me. I in particular chose in a way so that it is not like 0, 1, 2, this sort of thing. Okay. So, this index should be V1, this should be V1, 2 and so on. Okay. This is V1. Okay. So, the graph here, this vertex V1 has an edge to all other vertices, all other barycenters, this thing, all these face vertices that contain 1. So, in particular it should have a neighbor to V12, it should also have a neighbor to V01, it should also have a neighbor to V13 and so on. Okay. So, in particular we are looking at this example. So, we will carry on with this. Okay. So, V12 is this guy, its position is given by V1 plus V2 by 2. Okay. Its label is V12, but its position in the geometry, like in the Euclidean space, is given by this point V1 plus V2 by 2, correct. Okay. I mean this is definition. Okay. Now, again V12 has an edge to all those vertices, to all those faces that correspond to a superset of this. So, it should be in our picture, what should it be? V12, 0, 1, 2 in particular, right, but there should be, can be other things also. I am not going to draw it because 1, 2, 3 and so on, right, all these things. Okay. So, 0, 1, 2 and similarly 0, 1, 2, 3. Now, this thing that we have defined here, see I did not draw these edges, but they are obviously there, because this containment, set containment is a transitive relation, right. Similarly, if this guy is a neighbor of this edge, even though I did not draw it, actually exists and so on, correct, all this. Okay. Okay. So, now do you see that whenever I have a chain like this, it starts from a single vertex and ends with an entire vertex set, the whole thing, right, the indexing of this base simplex, they all define a clique, and each of those are maximum cliques. Yes, they are n size n plus 1 size clique. Yes or no? How many these things are there? This, so you will take all the vertices in this chain, right? There can be four of these things. Each chain can contain, each maximal chain can contain 4 such. I mean, when n is equal to 3, then it is 4. When n is general, it should be an n plus 1 size thing, correct? So, basically a maximal chain of this kind that I have drawn above, okay, chain corresponds to, when I say maximal chain, it has to be an n plus 1 length chain, right. It is to a clique of size n plus 1. Yes, and this has to be the maximum clique in the graph. Yes, do you guys agree? All of you on Zoom are awfully quiet. All this is clear, right, so far? Okay.
Because there is no vertex for an empty set.
Why is there no vertex? Why is there nothing for an empty set? What would empty set represent?
No, nothing. So in that case, the chain length will be n, right?
Why? So this is an n. This is an n sized. This is an n simplex drawn over n plus 1
okay.
points.
Yeah. All right. Okay.
Okay. So this is okay. So this is the point. Okay. This is an n simplex. N simplex means we are talking about in Rn. Okay. N simplex also means that those points on whose affine linearity we are talking about and all, there are n plus 1 of them. Okay. These are basic definitional things. If that is the case, this chain that starts from a singleton vertex. Okay. So, he is right. I mean, if we are talking about this subset in empty set is also this thing, but the point is the empty set does not have any sort of there is no interpretation of an empty set here. Okay. So, this is why we start with a singleton. So, singleton here was V1, of course, there could be a V, this would be a chain starting from V2, V3 and V0 also, right. Each one would start a chain of its own, and these chains might actually depending on what kind of sort of set you are looking at, which is containing one or the other, they will sort of intersect and so on and so forth. But the point is each one will describe a complete key, it will describe a maximum clique, and the clique has to be of that maximum clique is of size n plus 1. Okay. So, whenever I talk about maximum clique, this is what I mean. Okay. So, okay, right. Now, what is the subdivision, the barycentric subdivision? Okay. So, these are the vertices of my clique. Let us draw all of them as So, when I am going to subdivide a simplex, okay, basically you will see a nicer picture of this. Okay. So, I am just going to write it in words here, and you will see better pictures, much better than I can actually draw. That is why I even had some of this sort of thing. Simplex delta in delta 1. Okay. Have the property that delta 1 is the convex hull of the vertices of a maximum clique, okay, where this is some, there are several, is maximum.
Seminar.
What seminar?
Electromagnetism.
I think we were, was the class supposed to be here? I am sorry. I don't know, please ask somebody outside. We are doing, they are looking for a lounge or something. How do people? It's okay. Okay. Click in G delta. Okay. So, this, the notation is G defined with respect to this simplex and so on. Is this clear? So, this is how I am, so as I said, there can be many different subdivision. Our subdivision is defined like this. So, you take, you look at all these kinds of chains, from each of them there is an implied clique, maximum clique, and you look at the vertices of the maximum clique. Okay. When I say k n plus 1, I am talking about the vertex set. On those vertices, you look at the convex hull. That is what gives you the simplices of the subdivision. Okay. All right. Okay. All right. Now, I am just going to say a few, I have already said a lot of this thing. I am just going to define, this is a bit useful. There is the chain corresponds to a permutation. Okay. The permutation is defined like this. Whatever is, so this sort of a chain gives me a clique, it also sort of implies a permutation. Okay. Chain so each size is basically Si plus 1 and S0 is basically 1. Okay. So, this is this thing, yields permutation defined like this. So, pi of 1 is whatever was the index of S0. Okay. This. So, pi of 2 will be S1 minus S0. So, this is with respect to a general chain. In our example, pi 1, I am just going to write here 1. Let me write the pi here. Okay. So, pi 1 is 1, pi 2 is what? 2, correct. Pi 3 is, yes. Okay. That is the additional thing that is coming into this, and pi 4 is 3. Okay. I think the pi is in there. Okay, they are starting with pi 0, say, okay, ठीक है. All right. So, the indexing does not matter if you are trying to follow the, but I understand sometime at the beginning oftentimes what we are best able to do is sort of a something of a pattern matching, that is okay, but you know you should always keep in mind to extract the meaning out of it. Okay. All right. So, this is the permutation is important because it helps us to say how the division of items will be created and so on and so forth. Okay. So, what will happen is basically there is a subdivision, we are saying there is a way to do a subdivision which follows this formula, okay, this sort of a split by split and so on and so forth, and into, so the smaller and smaller triangles would be, the original triangle is let us say about V0, V1, V2, V3, the smaller triangles where we put the additional vertices will constitute of vertices of this kind, the internal, this sort of thing, and then we will draw triangles involving them. So, those are the smallest simplices as part of this subdivision. Those simplices, notice, right, they are n simplices, they are also triangles, right, they are basically three, there are 3 clique. At what is a triangle? It is a 3 clique, right. A 3 clique is what we are talking about here. So, every simplex, every 2 simplex is a triangle is a 3 clique. So, that is the thing, that is basically what this is in higher dimension. Okay. Now, this sort of a thing would generally be true even if we did not, like the subdivision, why these values come into play and so on, we will see later on, and what this permutation sort of, this kind of permutation gives us, but I hope that at least the picture of the subdivision and how they correspond to a complete graph makes sense. Okay. Now, when you have this n plus 1 clique, you know that each of these cliques actually can be colored with n plus 1 colors, right, there are only that many vertices. Okay. Each one individually can be colored with n plus 1 vertices. Now, the question is they are also colored, they can also be colored in a way so that they have good relationship between adjacent cliques. That is the interesting part, because haphazardly if I just were to look at a triangle, yes of course I can color this with this thing, but then there is another triangle sitting right next to it, right. Maybe over there it shares one edge with this graph, so it is properly colored, but what about a third edge, but the other 2 edges that it does not share with this, over there also some nice property holds and so on and so forth. That is the whole point.
We can keep subdividing until we reach a point where that kind of coloring is possible.
So, that is what we will do to prove that theorem, that we can always create smaller and smaller subdivisions for which. So, the idea is that triangle that I drew here, right, if I were to just divide a cake following this kind of a principle, this triangle, like I just take a point and split this thing, and each of these portions represents the value of the cake. Okay. That triangle that is down at the bottom, right, you guys can see, the people over Zoom cannot, but I hope you took a picture and so on. There each of the piece here is representing, let us say, the valuation. If I divide this, x represents a way to divide the cake such that this piece, okay, this object represents a valuation to this individual, this portion represents a valuation of that piece to this individual and so on. So, this itself is a cake division. Question is, they may not be happy because in this picture at least it seems like this guy is getting a really small piece. So, basically then the idea would be, oh, maybe I move this point a little down so that they all get a equitable piece. Maybe one in this thing it clearly seems very polarized towards this guy, right, this second diagram that I was drawing. So, maybe I shift it a bit to the right, bring down the point and therefore create a equitable division, envy free division. Okay. So, that is the intuition of it, that, and remember we are going to create. So, how to identify the point where that particular, that good envy free division lies. This is why we go smaller, create smaller and smaller subdivision to sort of identify that point. We know it lies somewhere in this big triangle, but where? Maybe there is a smaller triangle we identify, and so, okay, it is somewhere here, but it is still a very large bar. I do not still know where that point is, a smaller subdivision within it. Now, I have zeroed down my scope, it is like searching like you know, zooming in into a point. towards a smaller and smaller area to identify that right point. This is the big picture perspective. Okay, so this is the picture, that this part I think. So let's see this. Okay, this is the triangle and this is the tetrahedron. Let's go over this one by one. So this is the first simplex, this is itself the simplex, this is also a subdivision of itself, and so on. The first, after this, let's call this the first subdivision. The second subdivision would be the middle of this two. Vertex this plus this divided by 2 would be this. Vertex this plus this divided by 2 would be this. Similarly, vertex this plus this divided by 2 would be this. All the 3 vertices together divided by 3 would be this. Correct? Okay. Now, see this itself, now if I join these points, they are creating a subdivision of the kind that we want. Everybody, either they are completely disjoint or they share a face, right? They intersect only at a edge or a vertex. Okay. So now what is stopping us? We can further subdivide this triangle and create smaller triangles. So that's what this is. Okay. First we again subdivide this edge. These are these green thing, right? So basically each step 3 and so on, like in 2 steps, okay, 3 they are counting the this thing. Basically we create another sort of bunch of triangles and so on and so forth. Okay, so this is why iteratively you can now again you can apply this thing on this, right, smaller this and so on. Okay, all right. So I don't think I can say anything more as of now. We'll talk later about this. So now you see this is the same thing, this is happening here, but except that it's on a tetrahedron. Okay. So between V0 and V3, this is the barycenter, between this and this is the barycenter, and so on. And this is the barycenter for all these 3 black vertices, same sort of thing. Now this picture is basically saying I can create, now if I just zero in on this and this itself, yeah, oh the picture, yeah, this is fine. Okay, this 0, oh they do not have the 0, 1, 3, okay. So there is a 0, 1, 3 vertex missing here, which would be the barycenter of these 3 things, 0, this. Basically it would be the barycenter of this and this purple thing. Okay, this purple vertex, this is missing in this picture. Okay, maybe we move to here. This is the barycenter of this black guy, this guy, and this guy. So using this subdivided vertex and this subdivided vertex, basically we can see that we have they also constitute a tetrahedron, and therefore we can get all these sort of triangles from here. Okay. So similarly you can do this at the top, you can do at this bottom, and so you get this subsimplices. Okay. So now the interesting thing is, from the perspective of the chains, okay, what is the clique here? What's rather the chain, and therefore the clique. If you can just directly read off the clique, that is also fine. V0, V03, yeah, V0, 1, 2, 3, correct, yeah, correct. So that would be the clique. Similarly over here, so basically over here we start with V0 and create a clique. Over here we are starting with V2 and creating another n+1 clique, correct. That is the that's the point. Okay. All right. Now, okay, yes. Now this is where the coloring property comes in. Okay. Now if for any simplex on k vertices, so here we have a simplex on n vertices, this let delta be any subdivision of delta obtained by iterative barycentric subdivision. So this is the picture, and you can create much more smaller triangles, obviously you understand this. Now G delta will be G gamma be the graph whose edges are the one faces of this. So the one faces in a triangle, the one face has to be an edge, correct. So each of these are triangles, so we are talking about the one faces. Okay. So, now we are defining this graph g of gamma can, so whose edges are the faces of this. So, literally you can see the graph here itself. This graph is somewhat different from the graph that we were just now talking. I mean it's that graph here was defined with respect to the chains. The chains themselves describe subdivision. So, if we just start from the fact that the chains describe the subdivision, that subdivision itself is what we are calling the barycentric subdivision. Okay. So, a barycentric subdivision yields an object like this. So, now we are zeroing on the edges that we have created. So, whenever we see this sort of a thing, is basically what? It is a 3 complete graph, right, 3 click, and it can be colored with 3 colors. That is all this is saying. This is what this is saying, and what a proper coloring means, all vertices in each subsimplex have a different colors. Now, okay, so the point is, in the previous picture, the one that I actually okay, see what was happening here is the following. Okay, yeah, say again. How? Yeah, but it's the same thing. It's the same thing. So, this is defined in terms of the chains of the indices of the vertices that create this delta. This thing. See, the subdivision. These are the subdivided simplices. These are the collection of delta 1 is what is in gamma. Each delta 1 is uniquely described by some complete graph. A complete graph here in G delta, meaning a click in G delta, also describes a subdivision simplex. So, they are like in one-to-one correspondence. Okay. So, now yes, and now so when we are talking about the smaller simplex, we are basically talking about these objects and how their edges are interacting. Okay. So, what I am trying to see is okay. So, you can see the coloring here. Okay. So, as we identified, there was a chain involving 0, 3, 0, 0, 3, 0, 1, 3 and 0, 1, 2, 3, right. So, in that thing this would be the proper coloring, all vertices are getting different colors, right. Okay. Okay. So, this does picture, okay. They do not have pink there and so on, okay. All right. So, okay. So, the way to I wrote this down is because okay. So, they are using C1 okay. So, basically okay, in this picture just because we will be using the same the picture from the same book. So, it helps to remember what they are saying is that after the first subdivision was involve these black triangle, these gray edges, the sort of thick gray edges and so on. There the vertices were all colored this thing black, and then as we go further and further down, we create this smaller subsimplices and so on, and therefore, this is, so if I just look at the outside triangle as if that is the only subdivision we have not created anything, that could be colored with 3 colors, but now as we are zeroing on and smaller things, I no longer care about the coloring of the bigger vertex, but these sort of smaller triangles that are sort of sharing edges among each other.
So, this triangle was colored in like 2 levels, first subdivision and then second subdivision.
Yes, yes.
Can we generalize it like N simplex can be colored?
Yes. That is how exactly it is, like no matter how smaller and smaller you get. So, you can again further subdivide this and create another triangle, where basically this would be an intermediate some other color, right, and that color would be the whatever is the leftover color, correct. That is what this happened, no. Previously in that picture, what was this? This was the green, this two were black and this was green, then this got subdivided, right. We pretended that we have forgotten the outside big subsimplex. We have forgot at the beginning there was just this one simplex, then we created this midpoints, those were colored green, right, and then we ignore everything. Let us maybe just go back a step. Yes, here this one, top one, right. Initially it was this thing. we created this subdivision and created these smaller triangles. In those smaller triangles, this one is green, this is purple. This is a proper coloring, right. Now, we forget this thing, I am just going to subdivide this further. Okay. So, once I do this, I know what the smaller subdivisions here will not interact with subdivisions there because of the subdivision property that they cannot intersect beyond this vertex, right. So, what is happening here internally will not create conflict with coloring here. So, I can basically do this coloring thing locally within each smaller simplex. And how am I doing? So, this is again like as if this is recursively, this is one that big triangle. So, everything is colored black. The intermediate points here, this middle points here are green, and the point inside this is purple. That is what this is. Again, next step, you would basically zero in this smaller triangle and do this further. So, this is how I can create a coloring while I am subdividing. Okay. All right. Okay. Now, this is fine. Okay. So, now we need this definition of a proper labeling of a simplex. Okay. A labeling L of the vertices of an n simplex is proper if all these n plus 1 values are all different. So, those vertices that are creating the simplex, what was this? Firstly, they have to be affinely independent, and the convex hull of such affinely independent points is what defines a simplex. So, the color, the labeling of those points of the simplex have to be distinct. So, I am not talking about, there is a reason why we shifted from saying coloring to labeling. We are not talking about labeling. Okay. From the coloring, we will extract this thing called labeling, which has this additional property that there is a picture here. Oh, this has gone here. The labeling suppose this is a V1, V2, V3 triangle. So, L of V1 will be different from L of V2, will be different from L of V3. Okay. That is what this is. Okay. Now, what is a Sperner labeling of a subdivision? Okay, by the way, notice one thing. If you have a coloring, if you have a properly colored triangle, that is also a proper labeling, correct? Properly colored coloring means what? The colors are distinct, right? Proper coloring of a triangle means that the colors are all distinct. So, I can interpret that as a labeling also. Okay, all right. Now, we say a Sperner labeling of a subdivision is defined as follows. So, within an n simplex, I look at a subdivision. So, delta 1. So, L, the property of this labeling L within this thing should have this. Firstly, outside has to be properly labeled, the L of V0 to Vn, they must be distinct. All vertices within a subdivision are assigned labels. Again, you use the same labeling values as you would color the outside points, and when you restrict the labeling to any face of the simplex, that must also be a Sperner labeling, meaning it should be proper. Proper means what? That all the vertices, the simplex you are looking at, the vertices must be colored distinct, must be labeled distinctly. Within each subdivision, you use the same labels, but within any subdivision, see any face, again we always have this property, right? The faces will only intersect at points, or this is not a valid. Something like this, let us say. Okay, I should not draw this. So, LV1 is distinct from LV2 and distinct from LV3. Okay. Now, see over here I have a subsimplex here. This is a triangle, triangle, this is also a triangle, LV1 is taken here, LV2 is LV3, LV2 is taken here, correct. So, that leaves what for this? LV whatever this 3 is, correct. Yes. This one here, what can this color be? It should be LV2, right?
I have a question.
Yes. Tell me.
Why should the colors map to the VIs be distinct? It's not given in the definition, no? L of VIs, in case of a triangle, we can, okay, we have the, we have edge between all of them, and therefore all the L's should be distinctive.
Yes, I am trying to see what is reusable. I mean, we have to be able to reuse colors, that is part of this thing. No, first see proper labeling of a simplex. So, we agree that a labeling L of the vertices of an n simplex is proper if the L values assigned to each of those, let us call the base points, are distinct, are different, are all different means distinct, right. So, we need n plus 1.
Okay, I missed that, yeah.
Okay.
So sorry, I missed it.
So, the Sperner labeling is this sort of a recursive or iterative, this thing, however you want to call it. Outside you give, when you are dealing with this one big triangle, you give 3 distinct colors, right, because this is itself this big one is itself a simplex and it is drawn over V1, V2 and V3. So, they have to be distinct. Now, when I create, right, now when I create a subdivision of this, so a subdivision of, that is what I am trying to do, so that I am not creating wrong subdivisions, right. This is a correct subdivision, yeah. This is the center point. So, we draw this, this and this. Okay. Otherwise, we will look at a picture basically if I can't draw, if I make mistakes on my own. So, this is this. So, if I were to right, this is y, this is y. This is it. Okay, I should not. Why am I drawing the triangles wrong is what I am wondering. So, there is this thing here. This is the first subdivision, this, yeah, yes, correct, these are fine, no, please pay attention. If I draw incorrectly, then yeah, this is the part. No, so right. So, this is LV1. This is, so when I was here, this, so now this could be LV2, right? This point here. This would have to be, if this were LV3, this couldn't be LV3. So, we need another sort of a subdivision here and so on. Why should this be LV3? That is what you are saying? Because we had this triangle, right, this one, this one, this one and this one. So, these two, if this is LV2 and so on, what would, in order to, for this I could not repeat LV1 here and LV2 here. No, now it can be repeated, that is the point. Like after I have broken this, now it can be repeated, right. Previously, if I did not want to repeat, then I was following exactly. So, this sort of a way we can create. So, whenever sort of if I wanted to repeat a color, right, if they were like the same colors were appearing in this, subdividing that edge allowed me to repeat that color here, because I can use the third some other color here and so on. So, that is sort of the idea. Okay. So, let us see maybe a picture of a proper labeling and then we will figure it out from there. Okay. So, just the statement of Sperner, I will see it later on also. So, L be a Sperner labeling of the vertices in the subdivision, this is the follows this. Then the number of properly labeled simplices in the subdivision is odd. Okay. So, the point is, no matter how you label this internal vertices, there will always be a there will be at least one properly labeled triangle, and in fact there will be odd number of them, there will be 1, 3, 5 or so on and so forth. Okay. So, that is the thing. So, in fact it would be sort of impossible, can I not do this? So, suppose I repeated a color, okay, we can do this maybe later on this, it is kind of a fun exercise to see that how quickly we will end up with a, okay. Yes. So, this is an example of this. So, initially this is, oh, there are lots of colored actually, there are so many, everything is properly colored, right, in this example. No, everything is properly colored. Yeah, each simplex in tau has one black vertex, one purple vertex and one green vertex. Okay. All right. So, what are we doing now? Okay, so let us, before this we will now we will add some more details to this contour. Okay, so then we will see more definition. Okay, so let us see, this is where we are at. Okay, this is what this corollary is telling us. So, for interest, we do not have lot of time, I want to finish this class here. These are somewhat geometric proofs, but so I will just skip it, I will use them to infer the Sperner the result that we want to. So, this one was this earlier lemma, I forgot what it is, and this is the corollary, this is the one that is saying that allows us to say that they can be properly colored using n plus 1 colors. Okay. Now, I need more board space. Okay, so maybe this side. Okay. So, there exists, I am just going to for any greater than 0, there exists a subdivision tau of in which also so the diameter is this distance from the vertex, okay, is at most this eta. By this corollary, there exists a coloring using, let us say, so this delta is on the standard basis, okay, of n of them. Okay, so this is an n minus 1 simplex. So we need n colors only. Ring of vertices of tau. Okay. Okay. Now this is the thing, the association. If vertex Vi has color Cj, let us say. We say V owns Cj. Okay. Sorry, Cj, sorry, we say player, sorry, J owns vertex B. Okay. Yes, vertex V of the subdivision. The subdivision is being colored with n colors, right? Okay. All right. So now, okay. Now, okay. So now we will define the Sperner's labeling. I think the color actually does matter. Okay, labeling L of vertices of let me write of delta. Given a vertex x by its n coordinates. Okay, these are the values along the this thing EI vectors, right? The standard basis this thing. Define Bi to be Bix, sorry. Okay, I will tell you. There is a bit of a problem here, the notation, and it's I minus 1 does not actually make sense. 1 to I x k. So, I minus 1 b 0 x 0 does not make sense. So, this is for I greater than 2. V b 1 x is, let us say, 0 to x 1. Just a minute. Yeah, okay. So, this is, I am splitting. So, see, each xi here can only be between this thing. So, I am talking about, so delta is a is the simplex over this, right? Okay. So, the length of these vectors is 1. Okay. Now, so maybe a bit tricky to draw. This is the convex hull of let us say this is x vector y and z, right, when n equal to 3, correct. This is 1 1 1, okay. Sorry,
n minus 1 simplex.
Yes, n minus 1 simplex. So, this is a this thing, right. So, n equal to 3, it is basically what we are doing is a triangle. Okay. Yes, this is an n minus 1 simplex. Okay. So, I take a point, any point inside this. So, x, you basically see what its corresponding values are, coordinates are along each of these axes, right. That is what x 1, x 2, x n and so on are telling us. Now, using these values, I am basically splitting the k interval 0 1 in this way. So, the first agent, okay, B 1 for any point x, this is how I am going. So, I was saying, right, how each point in the simplex basically creates a partition. So, I am describing that. So, each for the agent 1 with respect to this point x, he gets the piece, let us say 0 to x 1. Agent 2 with respect to the point x gets the piece x 1 to x 2. Agent 3 gets x 2 to x 3 and so on. Okay? This is agent 1, agent 2, agent 3, agent 4. Okay, I have drawn too many, so I should not draw like this. Zero to x. Is this wrong? No, it should be fine. What is b n x according to this notation? Because this is how they have written, but I minus 1 does not make sense if I is 1, right. So, what is x 0 for instance? So, I interpreted that as this, but maybe this is this the correct? Maybe this is what they may, there is a typo there, because otherwise let us just go with b n x according to them is what, starting from x 1 to x n minus 1, right, and then all the way to x n, right. This is what their this is. So, if n is equal to 3, this should actually be equal to 1. If x 1 plus oh, okay, fine. So, just one. Yeah. Yes. So, this is how the splitting will be. This is correct. Okay. This is AG. So, this piece is basically x, I should not write it this way. This is x 1, this length is x 2, okay. This length is x 3. Of course, this length is also x 1 because I am counting from 0. So, my diagram was wrong, the way I was depicting. Okay. So, define this. Example for n equal to 3. Okay. So, this is how I divide it. Okay. Now, if maybe this picture and if player I okay, j because of the owns this vertex x, okay, this vertex x, and this player's j's preference. So, I basically am seeing, okay, who owns this player based on this coloring, some player owns this vertex, right, because this vertex got some color. So, that is what it means to be owns. If basically that is color of x is Cj, okay. I basically apply the valuation function of the player j to each of these pieces, the chunks, the blocks that I have created. Okay. If mu j of bk is maximal among all the pieces, meaning at least as good as this pieces, okay, this pieces, then what do you think should happen? L of what should be the labeling of x? Should be k. I see for any point what color it gets. The color indicates a player. Using the player's preference, there is a precise way of creating these chunks that depends on how the point is described in space, right, how x 1. So, every point has these coordinates. Based on the coordinates, I create these blocks. For each of these blocks, I basically see what is the player that owns this block, point preference for it. Whichever block is the highest, I extract that label and give that label to this point x. Okay? All right. Why is this a Sperner's labeling? Sanjay, is the definition clear? Is the question clear? Is that, I mean, Sperner's labeling. So, I will just show you the definition of Sperner's labeling and tell me, is this clear why it should be a Sperner's labeling? I should not write, I should write this thing. B1, B3, okay. Claim this is a valid, look at that assumption. Okay. So, think about this, why this is true. Okay. It is not hard at all, you can sort of do this. Now, let us see a diagram. What should be mapped to a, no, I am talking about a valid Sperner's labeling. This is the thing that is giving the labeling. So, the labeling is a function from the vertices of the subdivision to what? In this case n plus n colors. So, some values, not colors, some values, let us say, let us just put it this only, it is fine. Right. So, this is a index, no, k is an index. So, using the coloring function and the mu j function, which was the preference of the which told us what is the preference of this thing. Remember, this was basically given as f of j, the starting whatever the block, the end point of this is, basically however we are describing this, right, f of j applied to this minus f of j applied to this. That is what this valuation function was, right, the f of j of the right end point minus the f of j of the left end point, that is what this was. But it does not matter, whatever mu j is, I do not need to think how it comes, whatever mu j is, I know there is something that is the largest of value, I extract, I see there can be multiple, just see the one that pick up one index and apply this. This is a valid Sperner's labeling. Okay. Okay. So, once this is true, now, so what does Sperner's lemma says? It says that once you have a Sperner's labeling, it is implicit that we are talking about a valid Sperner's labeling, then there exists an odd number of properly labeled simplices. Okay. by Sperner's lemma, there exists properly labeled, there exists odd number of in the subdivided collection, correct? Okay. Yes, this is just a statement of Sperner's lemma. So, all I did was this is a valid Sperner's labeling on the vertices of gamma, right. Now, I am applying Sperner's lemma on this labeled vertex of this thing, right. That once I apply Sperner's lemma, I know that there should be an odd number of properly labeled simplices. So, I am not proving anything, whatever this was the one that requires a proof. It is just a very small argument why this is a valid Sperner's labeling. Use the definition of Sperner's lemma, see the assumption and sort of keep this picture in mind, like how we created this, like basically the definition of the labeling. You need the definition of the labeling assumption, and please do prove it. Okay. Okay. So, we will put this in the homework, okay, the homework one. It should be out by early next week. Okay. So, now we will just have to go a little bit faster, and then I will try to, I need 15 more minutes maybe, and then we should be done. Okay, let us see a picture of what the Sperner's labeling is actually trying to tell us. Unless you can tell me, what do you think, given the way I have described to you the Sperner's labeling, can you tell me what is it actually going to capture?
You are trying to zero in on the point which will subdivide the simplices into NV fading.
Yes, that is a big picture, but the point is, how does this labeling get us across the line, or like get us closer to that objective?
Odd numbers means there exists, like there exists at least one.
Yes.
We
Okay.
go inside that simplex and maybe repeat this process to
Okay, but that particular simplex, that properly labeled simplex, what information is it telling us?
The color tells who will not envy others for sure.
Sorry, Sanjay, some of your words got garbled. Can you please repeat?
It seems to tell that the color of a vertex is corresponding to the agent who will not envy for sure.
Okay, and the labeling tells us? See, there is a coloring tells us this point sort of is owned by someone, which means something, but the labeling tells us a little bit more information. Okay, go back to that mental picture. A point describes a partition of the simplex. We are trying to identify that right kind of point. That point is owned by somebody, correct? That point is now being labeled by the piece. If I divide the cake according to that point, which is this type of thing, the labeling on that vertex now tells me what is the which piece of this portion is most liked by that guy, by that player who owns it, correct? Yes. So, okay. So, now what Sanjay is saying, that Sanjay, you are saying that now nobody will envy this guy.
this person wanted to.
Yes, yes. If that person particularly gets this piece, right, this portion from the cake, he is not going to envy anybody. Now, the point is, okay, he is not envying anybody, but what about other people envying each other? Within this point, close to it, perhaps we can create another simplex within which there is another vertex, right, for which there is another that is colored by somebody, that is owned by some other person. From there, I extract a labeling such that that guy will again not be envied by any, he will not envy anybody. So, step by step I identify a point, right, where basically at least one person is at least as happy as all the other, right. So, keeping that idea sort of zero down it and using this, so that you will see the continuity and so on, there is a point close by such that nobody, first guy did not envy anybody at the very first step, then the second person also does not envy, and then nobody basically envies anybody. And okay, so there are details, so let us just slightly try to address some of these things. A picture would probably help here to see how this, yes, this one, okay. So, this is the coordinates of x is the, where is the x? Yeah. So, this is the 3 vertex, think of it as the standard base, the vertices pointed by the standard basis. This is the first one, the top one, label 1, label 2, label 3. Okay. Now, looking at this, okay, so I probably should have pointed this out. When you have a value 0, correct, the base, your here or each time. So, let us look at this example here. When you have the point, let us say is what is this on this, yeah. So, let us look at this point, okay, where you have x is basically x1 0 x3. So, such a point b0 b1 of this point would be 0 to x1, b2 of this point would be what? Well, x1 to again x1, because x2 is 0, right. b3 of x would be, well, x1 to x3, correct, because this x2 is 0. So, now tell me this thing. So, one of these, so either, so what should be the labeling of this vertex according to L? See, either it would, he would prefer this piece or this piece, right. So, labeling is therefore, so L of x should either, could either be anybody, either 1 or 3. So, that is what this basically is. All those coordinates for which you have a non-zero value are the potential labels for you, okay. And so, when we identify a simplex which has all distinct labelings, right, what is it saying then? This is something different from this, different from this, means what? Each of these people can be given a distinct piece of cake, nobody is fighting over the same piece. Each one has a distinct favorite.
Okay, no two people have the same.
Yes. Otherwise, we should be able to, yeah, that is there, but I am saying suppose we do find such a triangle which is properly colored, which is properly labeled. A properly labeled triangle means what? All the colors are distinct, right. So, it means what? That this person is has a preference for L1 the piece 1, meaning if he gets piece 1, he will not envy anybody. Maybe he likes piece 1 and piece 3 equally, but the fact that we have given him label L1 and this person L2 and L3, this person gets L1 means he is at least as happy with this piece first chunk as anything else. So, he will not envy anybody. This person is happy, at least as happy with chunk 2, this person is happy with chunk 3. So, therefore, nobody is envying anybody. This is the takeaway, okay. All right.
Why does we say the odd one if there exists by Sperner's lemma? We have the fact that the number of subdivisions will be odd.
Okay, Sperner's lemma tells us this was the argument. So, we saw it in 2 dimensions, how we can create. You can create a colorful triangle outside and travel through this and identify another this thing. It is like finding for every source there is a sink, right. So, you create a source outside and using a directed path argument using, so either the moment you enter this, either you have found a triangle or itself a colorful triangle, fine, else you will have an edge which has a, let us say whatever edge you travel across, whatever green and black. So, you will have an edge which has green on the left hand side and black on the right hand side. You travel through that and find basically that is a door through which you go and so on. Anytime this sort of thing goes on, you will be able to identify. So, they exist in, so each source will have a sink in a graph which has in degree, out degree at most 1, right. They will always, these unbalanced vertices exist, therefore, they exist in pairs. Now, the outside one is the artificially created thing that you did, right. So, if you remove it, what will you get? You will get an odd number of objects inside. So, that is sort of the idea of why it is odd, but in this case what we need is that there exists one and therefore, the argument sort of goes through. Okay. So, now I do not know how much more I can finish. Which part? I am just going to delete this portion. Okay. So, next week the result I want to show is the following, that let epsilon be 0, okay, maybe I will just take 5. There exists eta greater than 0, okay, such it is that if maximal diameter of all simplices, it's, these were part of our assumption that we is less than, you will see why this is needed now, eta, then any vertex x of a fully labeled, meaning a valid labeled simplex in tau, means this is a Sperner label. Okay. Determines epsilon NP free division. Okay. Let delta star simplex and owned by I, okay, player I. Therefore, basically color of delta star is I. Okay. This is a vertex, right? The color of sorry, I am mixing. This is these are these points, okay, such that V I by player I. Okay. So, what I have done is there was a fully colored simplex, okay. There was a this thing. I can relabel the vertices as if this vertex vi is owned by player I and so on, right. The coloring was this thing and so on. Okay. So, this is the thing. Okay. So, now okay, let x, this x so this point determine, I will tell you what the partition B1 to Bn, okay, defined like that. Now, this I will define the permutation k to be the label of the vertex of Vk. So, this vertex Vk has some labeling, it has color I and it also has a labeling, correct, each one has this Sperner's labeling. So, I am going to define this permutation of k, permutation is from 1 to n, it is defined, and for this value k I am going to define this to be this. Okay. All right. So, okay, let me just write this down. Okay. Now, tau is fully labeled, meaning it uses all the colors and so on, implies this relation, right, implies pi is a permutation. Otherwise, the way I have defined right now, I have just given a, basically permutation means injective map, okay, that is what it means. When you say permutation like this, it means some injective map. 1 to 1. For each k, assign to player k piece is defined as B of pi k, which is same thing as saying k. Okay. Let me just wait. Okay, I am going to just write it, claim this is an epsilon NV free division for sufficiently small okay, there exists an eta, okay, for which this is an epsilon fair division, okay, because you can create smaller and smaller subdivisions, therefore, but this will show that there exists an eta for which this will be an epsilon NV free division, okay. All right. So, now let us just go take a step back and say what is actually happening, okay, how I am creating this. So, delta, we have a completely defined labeled simplex, delta star is the simplex that is sort of given by Sperner's lemma. Now, we know there is at least one because there is an odd number of them and blah blah blah, and the labeling inside of this is such that we assume that the player, it does not happen, I mean without loss of generality, this vertex Vi is owned by the player I, meaning the coloring is color Ci. Okay. Now, we determined Okay, this vertex x, okay, yeah. Okay. So, x is some point, okay. Not point, it is a vertex of this simplex. So, I associate, I say x is actually equal to V1. I do not see how this is particularly useful, but okay. Let us, without generality, we can assume that we are talking about V1, okay, because we are trying to prove that any vertex within this also gives. So, again go back to the picture that a vertex actually defines a partition of the simplex, and that allows us to define a cake division like that, right. That was the picture, that is what we saw before. So, we are just trying to formalize this, that why that is actually true. So, any vertex over here, so you know the coloring association. So, for this vertex V1, we are going to basically determine this partition B1 Bn like that. So, you will assign the label to this guy, you will assign the label that label of that piece that gives him his favorite piece part. Okay. So, for each player k, okay. So, now I am going to define this function pi to say this, okay. Did not really need it, but okay. Pi is this thing. So, every index, so this is a player, okay. Pi is a function from, let us say, the player set to the some label of a, I do not think this helps actually, not sure, just one second. I am trying to go fast, and in this pi of k, okay. Okay, because this is a fully labeled simplex, labeled in terms of this thing. So, you know that no labeling, no vertex will get the same repeat, everybody gets a distinct label and so on and so forth. So, therefore, pi is a one-to-one definition, right. Pi is basically take k and take the labeling of V of k. V of k is the vertex set of this simplex, okay, the vertices that constitute this simplex. So, this is fine. Now, for each player, to this player k, we will assign this piece. When we divide this cake, basically, we are going to assign that B chunk, which is labeled with this vertex, this his label, the Sperner's labeling of the kth vertex. Give to player k the piece what did I lose? I lost my concentration, I lost something. Okay. Okay, okay, okay. See, L of V k piece most preferred by whom? By k. No, 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 no. Yes, piece most preferred by the player who owns Vk, which happens to be player k, right? That is the thing, yeah. Who owns Vk? This is why sort of this sort of thing helps. Who owns k? That is k. Okay. This is the labeling that tells me this. This is why when I give this piece, this chunk, right, that bth chunk to that player k, he does not envy anybody. Okay. I mean that is the point here. Okay. So, now, so okay, the first proof, this is clearly each I prefers his piece as much as this sort of a thing, right, as much as anything piece. Okay, or rather here what did you say? I does not envy anybody, right? I anybody. I think I made a mistake here. So, I am okay, good, right. Okay, sorry. So, first I am doing this partition from the perspective of this one, okay, V1 from the vertex V1 determines the partition, that is the way this is. So, when I feed these pieces basically to this to the player that owns this color, which is color 1, right, player 1, he points based on this which is his favorite piece, right, which is his favorite chunk. So, the label of LV1 would be best piece from V1's from player 1's perspective, correct? Yes or no? Because who am I asking for the opinion? The color who owns this piece, right? The player who owns this piece. V1 is owned by player 1, V2 is owned by player 2, V3 is player and so on and so forth. So, Vi is owned by player I, and therefore, L of Vi tells you the best piece from the perspective of player I. Best piece. So, L of Vi will tell you that if I divide the cake from the I's perspective, which piece actually is the favorite of the player I, okay, best piece from for Pi. Oh, sorry, unnecessarily messed this thing up. So, whenever I do this sort of a division, I can sort of extract based on this thing what the that person's perspective is. Okay. Now, because this is a because the coloring was proper, each one did get a distinct color, right. Each of these vertex is owned by a distinct person, player 1, player 2 and player n. Therefore, if I subdivide this thing, I will get some opinion based on their favorite piece of this. The L itself is a valid coloring. Therefore, they are basically all telling a distinct, they are all pointing to a distinct piece. So, the fact that there exists a fully labeled simplex, that comes from Sperner's lemma. right. Why am I getting a fully labeled simplex? Because of Sperner's lemma. Within that simplex, I have assumed that each one is owned by a unique color, because it is this thing, and from there I am sort of trying to extract this meaningful this, that everybody can actually get simultaneously get a piece that they like, but there is something missing here. Can you tell me what that is?
We have to tell one allocation to give to everyone. We are talking about different allocations where each person gets a part that he likes.
Correct. So, the point is simultaneously this can be attained for each individual is what we have to show. So, but here is the thing. Yes, okay, let me say this. This is small, not very, the diameter plays the role here. So, this is V1, V2, V3, okay. Because the diameter of this is small, at most eta, V1 and V2's preference, meaning if I think about V1 as being a set of coordinates, right, and this is y1, y2, y3, they are not far, okay. Yes, so basically if we are close to satisfying V1's this thing, we can't be too far from, that is the sort of idea, but
because till now we don't see any significance of epsilon because we have created.
Yeah. Okay, so you know what, I think I am going to, I do not think I can give a very clean picture of this now. Let me see, we will finish this at the very beginning of the next class. I do not think I can take a extra class, but we will finish this, okay. There is some subtle details here that I do not want to gloss over, because that is the part, that is the proof, okay. So, go over this, see if you do not follow, I will answer any questions if you have, but I will finish this part of the proof next time I see you, okay. All right, do you guys have any questions? Then else we will stop now.